Hi everyone, today's question is from the chapter of Gravitation. This question is asked by one of my students and it's a good question because it involves multiple concepts. So let's see what the question says. A satellite of mass small m is launched vertically upward with initial speed u from the surface of Earth. After it reaches height capital R. Now what is capital R? They have mentioned it is radius of Earth. It ejects a rocket of mass small m divided by 10. So mass of the rocket is 1/10 of the mass of satellite, right? So that what happens after that? They told so that subsequently the satellite moves in a circular orbit. We have to find the kinetic energy of the rocket. The options are in terms of small m, which was mass of the satellite, capital M, which is mass of the Earth, and capital R, which is radius of Earth, and small u, which is the initial speed given to the satellite from the surface of Earth. Okay. Now, as I told you, this question requires multiple concepts, right? So let us quickly revise those concepts. The first concept is of conservation of mechanical energy, and it says if there are only conservative forces which are doing work on the system. Now by conservative forces, what do we mean? It could be gravitational force, it could be spring force, and in second PU you also learned it could be electrostatic force. So if only these forces are doing work, then we can use this formula, which is basically saying the total mechanical energy. Mechanical energy means sum of kinetic and potential energy, that should remain constant. So the initial sum of kinetic and potential should be equal to final sum of kinetic energy and potential energy. So this is something we should know. Now what is the formula for gravitational potential energy? Well, if you have a spherical body and a small body, let's say the mass is small m, this is capital M, and the center to center separation is small r, then the gravitational potential energy, which we study in the gravitation chapter in first PU, is minus G capital M small m by r. The minus sign basically means the force is attractive. Okay. The second thing you should be knowing is something called conservation of momentum. Let us understand this through an example. So imagine you have a bullet and a gun system. Okay. So this is bullet and gun system. Right now it is at rest. Bullet's mass is small m, gun's mass is capital M. So right now it is at rest. Now when you fire the bullet goes forward. What happens to the gun? Well, the gun recoils backward, isn't it? It recoils backward. So the reason why it recoils backward is from here to here this process happened very fast. So it happened so fast that forces like gravity can be neglected. So if forces like gravity can be neglected, then I can assume there is no external force. And according to this, if external force is not present, then momentum of the system should be constant. So what is the momentum of this system? It was at rest. So this is zero momentum. So therefore final momentum also should be zero. Therefore if this has positive momentum plus mv, this should have negative momentum minus capital mv. So that when you add these two, you should still get zero. So the total momentum of the system after the firing should be equal to total momentum of the system before firing, and that is because the process happened very fast. Okay. Now the example of bullet and gun was in one dimension. What if let us say there is two-dimensional motion where one can go this side and another part can go some other direction? Then what will happen? So imagine there is a body with mass m which is initially having velocity this side. So it will have momentum this side. Let's say p. Now it breaks. Suddenly it breaks. Fast process. And I told you in fast process gravity can be neglected. So you can use conservation of momentum. Now let us say it this somebody says that this mass breaks into these two parts, 1 and 2. Is it possible? Think carefully. It is not possible because final momentum and initial momentum should be same. Initial momentum is only along y-axis, but final momentum is along x-axis also, y-axis also. So how this momentum came? Correct? No. So therefore this is not possible. So if part 1 is going this side, part 2 must go somewhere here. Why? So that this part will have two components, right? So you can divide this momentum into two components. Now see what will happen. This momentum and this momentum should cancel. Then initial momentum is along y-axis, final momentum is also along y-axis. Then it is possible. The last part you should be knowing is about orbital velocity. So imagine there is a satellite which is revolving around Earth in a circular orbit. Then whatever force is acting on the satellite, the gravitational force, that should be equal to ma from Newton's second law. Now what is gravitational force? Capital G, mass of Earth, mass of satellite divided by distance from center to center. That is nothing but radius of the orbit, right? And this acceleration will be centripetal acceleration, which is velocity squared by radius. So one radius gets cancelled, m gets cancelled. So the velocity with which the satellite orbits the planet, here in this case Earth, that velocity, orbital velocity, is root over gm by r. Where r, remember, is not radius of Earth, it is radius of orbit. So this formula is also very standard. Every JEE student should be knowing this, right? Now let us come back to the original question. After understanding those concepts, you will find this question is so simple. So let us see what the question said. Here is Earth, whose mass is m, radius is r. From the surface of Earth, a satellite is projected with what speed? U. And when it reaches some height which is equal to this radius, they told a rocket is ejected from the satellite. Now this is very similar to bullet coming out from the gun. So you understood there you have to use conservation of momentum. But before the rocket was projected, we need to know what was the velocity here, right? So let us calculate this velocity first, before the rocket was projected. So to find velocity here, from here to here you can see the only force acting is gravity, and therefore we can use conservation of mechanical energy because gravity is a conservative force. So what is the kinetic energy here? Half m u square. What is potential energy here? Minus g m m by center to center distance is capital R. That should be equal to kinetic energy here, which is half m v square, plus potential energy here, but potential energy is minus, so minus g m m by center to center distance is how much here? 2r. Right? So let us calculate V. First of all, small m gets cancelled. Let's multiply with 2. So we multiply with 2, this half will cancel, this 2 will come here, this half will cancel, and this half will cancel. Right? Then what will I do? I will bring this minus gm by r this side. So gm by r plus this u square minus 2 gm by r will be equal to v square. So v will be this gm by r minus 2 gm by r will be minus gm by r. So root over u square plus 1 minus 2 is minus 1. So minus 1 gm by r. So this is your velocity when the satellite reaches this height. Let me mention it somewhere here. Right? Okay. Now see what they have done. When this satellite of mass m reached here, they told a rocket is projected. Where it is projected, what is the speed of the rocket, nothing they have told. But one thing they told, after the rocket is projected, the remaining satellite moves in a circular orbit, they told. Now, if it moves in a circular orbit at this height, then its orbital velocity will be how much? Root over, what was the formula we derived? Gm by radius of the orbit. What is radius of the orbit? 2r. Now what is the mass of this satellite now? Remember, m by 10 was mass of the rocket. So that has been ejected. So remaining mass will be what? 9m by 10. Isn't it? M minus m by 10. 9m by 10. So this satellite's mass is now 9m by 10. Now, remember, momentum before and after should be same. because this rocket was projected fast. This is a sudden process. So gravity can be neglected, I told, in sudden processes. So students, here momentum is vertically up. Now here we know the one part of the system, which is the remaining satellite, that has momentum this side. So it is very clear, like I explained in the previous example, our rocket should have one momentum this side, one momentum this side, so that it will cancel this momentum, and there should be one more momentum this side, isn't it? That means our rocket should have one velocity this Vx, let me write, and one velocity here Vy. What is Vx and Vy? These are the components of velocity of rocket. How I came to know these two must be the components? Because initial momentum is along y-axis, remember. Therefore, final momentum also should be along y-axis. But here's the remaining satellite is moving in circular orbit. So it will have tangential velocity, isn't it? This orbital velocity. So to cancel this momentum, our satellite should have one component of momentum this side. And there must be one more component this side. Remember, this mass is m by 10. Right? Now let us use conservation of momentum. First let me use along x-axis. Okay, this line I am calling x, and therefore this will be y. So along x-axis, if I use conservation of momentum, what will I get? Remember, here there is no momentum along x-axis, right? So therefore this momentum and this momentum should cancel. So momentum of this will be what? Rocket's momentum along x-axis. Mass into this velocity. And that should balance this momentum. What is this momentum? Mass of rocket. This is mass of satellite, okay, not rocket. Into velocity of rocket along x-axis, which we don't know. So m gets cancelled, 10 gets cancelled. So the x component of the rocket's velocity is 9v0. And v0 we know is root over gm by 2r. So let me mention that here. 9 root over gm by 2r. Now let us use conservation of momentum along y-axis. So what was the initial momentum of this system along y-axis? M into v, right? This is the only momentum. And what about this system? Well, only momentum will be due to Vy, right? So mass is, remember, the rocket's mass is m by 10. M by 10 into velocity is Vy. M gets cancelled. So Vy is 10v. So Vy is 10v, and v, remember, is this. Okay. So once you know the x and y component of rocket's velocity, what will be rocket's velocity? X component square plus y component square, right? So the kinetic energy of rocket, which we are supposed to find, will be half into mass of rocket is m by 10 into velocity of rocket square. So m by 20. Velocity of rocket square, if you do, will be vx square plus vy square. So now you just have to do the mathematics part, right? So vx square means this square, it will be 81 gm by 2r plus vy square will be 10 v square. 10 v square will be what? 100 v square, and v square is this. So 100 into u square minus 100 into gm by r, right? So I hope this much you can do, right? Just substitute this v here and then square it and substitute here. So this will give you m by 20. So 81 by 2 minus 100, gm by r is common. So 81 by 2 here minus 100. That will be 281 minus 200. So minus 119 by 2. Am I right? Yes. So it will be, let me write this way. So this minus this will be, first let me write this one, 100 u square, and this minus this is how much? Minus 119 by 2 gm by r. Now in the options, if you see, there only u square. So let me take 100 common. So if you take 100 common, here you have to divide by 100 because there is no 100 here in the numerator. So this will give you m by 100 here, 20 here will be 5m, right? 5m u square minus 119 gm by 2 into 100, 200. This is your option B.